Yes. I once again welcoming you all of you the lecture series of electrical power quality. So in the previous lectures we are discussed so many things regarding the distributed generation and all other things. Now we are at the middle of the concept or topic like operating conflicts in the power system due to the addition of some distributed generating units in the power system. Okay, now we are already discussing some topics about this one. Now in the remaining we'll see this. Okay, okay, so here see that. Yes, first one. So we are we are already completed the topics like utility system, utility fault clearing requirements, reclosing, and interference with the relaying. One specific subtopic is there. Then after you can go for the voltage regulation issues and things. Okay, today class. Today we are going to discuss voltage regulation issues and a small part in harmonics as well as a small part in inference with the relay. Okay, now you can see this inference with the relaying. So in this we can divide it into the three different types. First one is reduction of reach. Second one is feeder breaker tripping, and third one is fuse save. A very important thing. So now see here in this one, in this topic. Now you can see what is the reduction of reach. We are already discussed in last class, but once again you can see that what is reduction of reach. So now see this. You can observe this red circle. This is the actual relaying identifying capability range. So this is the normal production. Relaying the relay's ability to identify any faults in this range. Okay, because this we can call it as the reach. Because of it adding. Okay, because of adding. Okay, some DC into the system. Now this is the DC into the system. The current. Here we are discussing about the power current relay. Okay, the current capability, the current measuring capability. Yeah, remember the current measuring capability of the release reduced. Okay, if there is any fault in this region, it is unable to identify that fault. So this is, you can call it as the reduction of reach. So these are the some solutions to reduce the reduction of the reach. Okay, then what is the next one? We are already completed. What is the next one? The feeder breakers. Yes, see this feeder breaker. Which breaker? So here they can consider the one example. They can consider the one DC 2 megawatt DC, which is connected one of the feeder 2, feeder 1 and feeder 2. It is connected in feeder 2. So while these are the circuit breakers. Circuit breaker, feeder circuit breaker 1 and as well as feeder circuit breaker 2. Circuit breaker 1, circuit breaker 2. If there is any fault is occurred in this feeder 2, what will happen here? First thing is fuse is going to melt that one, then coming to the recloser, then after the circuit breaker is open the circuit breaker. So now see this in this type of the fault, you can see this. For example, in this case, in this diagram, they can assume that the fault in the feeder 1. We are connected. Okay, see this example carefully. We are connected DC in the feeder 2, but they can assume that for suppose there is any fault in the feeder 1. What will happen here? What will happen here? If for suppose this the fault in that fader one, nothing but the circuit breaker one is ability to clear that fault. Okay, if it is failed to clear that fault, it is coming to the fader two. But this fault is cleared in this section only. In this section only. So, but suppose it is failed, that will not will happen here. The circuit breaker two, not in present in the fader two, is operated to clear the fault. So this is the systematic tripping of the or sympathetic tripping of the faders. So now series what we left in the last class is the defeat of fuse saving. Okay, what is this fuse saving? And now see, again we can see this diagram where this is the fuse. Now we can call this as the fuse. This is the fuse. In the name itself, it gives some answer here. Fuse saving. So here, how we can save the fuse from the overcurrent. So overcurrent protection now. So remember, we are talking these three categories of the faults or problems based on the overcurrent protection only. Remember this one, overcurrent protection. Okay. Okay. Now see this. For suppose there is a fault in this fader. There is a fault in this fader. Oh, what is our aim? What is our aim? A fuse for purpose is to save the fuse. Our purpose is to save the fuse. For suppose, if there is a fault in this fader, remember you can assume that there is a fault in this fader. What will happen here? The fader connected fuse is melted and open the and as well as clear the fault. Or suppose you can restore the power again. You can restore the supply or again. What will happen here? A man is coming to this place and replace this fuse. So it will take lot of time. First one, okay. Second one, it will take some costly. Okay, so it will so more impact on the economical way also. So one person is coming to this place and observe that and replace this piece. It will take a lot of time to restore the power. So that's why here there is a one small technique they can follow here. You can observe this feeder, this one. We are connected the DC also. Remember, you can observe this. When observe this carefully, you can connect it the DC also. Now see this. What is the capacity of this DC? The DC capacity is 5000 kilowatt. Okay, so here our fundamental procedure is, or our aim is to save the fuse, even though there is a considerable amount of fault. Okay, and that time, so first a recloser. This is the recloser will open to clear the fault. Recloser, recloser. You can design the system is like that. Okay, why? Whenever the fuse is burning, the fuse is melt, it will take some time, and that time some amount of, remember, some amount of current is passing, or current is passed through this region. So on that one, the recloser on that region, the recloser is sensing that fault and clear the fault. Once that is opened, so there may be a chance that we are saving the fuse to not be melt. Okay, this is the one of the way to uh, to increase the to save the fuse. Nothing but before opening or before melting of the fuse, so to open the recloser, that is the one thing, one point here on saving point of the fuse. What is the second one? there are some different solutions to saving the fuse here. What are the solutions? We have three different solutions to save this fuse, to defeat the fuse from fault conditions. See, first one, to increase the size of the fuses. Nothing but to increase the size means here. What is the size means here? Not this one. The rating of the fuse. To increase the rating of the fuse. Okay, or then what is the second one? Second point, what is the second point? To particularly these are not connected to the intermediate. So choose to simply abandon fuse saving, particularly if the fuse is not. So like here, we can assume this as a second case. So before melting or before defeat of this fuse, the reclose is open. Here, then what is third one? To use some transformer to connect this DC. Here, see this require DC to have transformer connections that do not feed single line to ground faults. For suppose if you are installing here, see this, all of you see this red color. For suppose if you are installing, see this, installing and transformer to this DC. Nothing. What is the meaning of this one? Through this transformer only, you are connecting this DC to the feeder. So that will greatly impact the fuse saving. So in which way? So it will reduce us the, it will not feed the single line to ground fault. So in this way, it may be to protect the fuse from the different types of the faults. These are the different solutions. Okay. Then you can see the most important one. Most important one. Next, voltage regulation issues. You can see this this side. Voltage regulation issues. You can see this. Voltage regulation. You know that what is voltage regulation? Sending in voltage. Now see this. So sending in voltage. Okay, this is sending in voltage. This is the receiving in voltage. The difference between these two will indicates the voltage regulation. Percentage voltage regulation. Voltage regulation. So sending in voltage minus receiving end voltage by sending in voltage with respect to we are calculated in sending end are divided by VR with respect to we are calculated in the receiving end side. Based on that has two phenomena you have. So based on you can calculate based on VS way, or you can see the sending in for personal voltage regulation in sending in way. On that time we can divide it by VS, and you can know the percentage voltage regulation of receiving end side. So we can see this way. So on that time we can measure the divided by VR, whatever we can give the approximately the same values. But this difference, whenever this difference is more, sending end to the receiving end, that means so this line or this feeder or this section of the power system has more losses. So where you can get the less voltage levels, for example, VS minus VR, VS minus VR, that means VS minus VR. So for suppose it is 130 volts VS, it is a for suppose 120 volts. Then what is the percentage voltage regulation? Nearly of this one divided by 120. This is the gap. 10% voltage gap is there. 10% voltage gap is there. Okay. So to reduce this the 10% voltage gap. Okay, to reduce this 10%. For example, I just say that 10% voltage gap. So one solution is to improve the receiving end. Receiving end side voltage. So this way. So one of the solution is to improve the. This is the sending end VS. This is the receiving end VR. This side, this receiving side, we can improve the voltage. So by means of we can add the some DC. Yes, see this. We can add the some DC. To withstand the to drive the load from the distribution side or load side, we can add the some DCs to this side. So in this case, what will happen here? So this is the curve to represents the under normal working condition. So this is the voltage profile curve. So this is the region. So this is the sending end side. This is sending end. This is receiving end. So by sending end to receiving end, there is some fall in the voltage levels because of some losses, some transmission losses, or some distribution losses, some additional factors. To improve this region, yes, to improve this region. Okay, you can add some DC. This is the normal working condition. So you can improve this one, this voltage regulation gap. Now see this, you can start the voltage. Yes, our sending in voltage is here in this line. This is the line. Our receiving in voltage, you can see, observe this. Our receiving in voltage is here in this one. Here it is present in it. So this is the gap. You can fill up this gap. We are using, and you can add this gap, or we can fill this gap. We can use this DC to fill this. DC distributed generator. Here, there are different types of distributed generators. I'm not going that one here. So you just add this some distributed generator to improve the receiving end voltage, to increase the level of the receiving end voltage. Okay, this is the case. For suppose, for suppose, for suppose. So this is under normal working conditions. For suppose. So when you add this DC to the system, that's DC, DC Vs. This is VR. Can add DC to this system to improve the power quality. But suppose due to the some additional factors, also due to some external faults, some external impacts, suddenly DC is disconnected from this system, from this line. What will happen here? You understand? You understand? So this is under normal working condition. This is under normal working condition. Okay, so this is the fault case. This is the fault case. Let's see this. For suppose there is some any fault, or there is some any external fault or internal fault, whatever it may be. Suddenly you can remove this DC to this line. What will happen here? The voltage at sending end to the receiving end level is increases, sorry, decreases very rapid. Now see this, here see this, this is the way. Now see this, so this bottom line is also crossed this way. This. That means here, for suppose this is 100 volts, 100 volts. So you can imagine, for suppose this is 100 volts. To improve this one, this is for example 80 volts. To improve this one, you can add the some DC. So again 100 volts. This is the 80 volts. So to improve, you can add this one. So it may be maintained to the 90 to 95 volts under this. So due to some external fault, you can suddenly remove this DC. It will fall to the 60% of that level. I may not say that, or I am not sure that these are the constant level, but for our explanation purpose, we can our simplicity purpose, we can assume this levels only. You remember? Okay, this levels, this percentage levels are not fixed. For our simplicity purpose, our explanation purpose, or easy understanding purpose only, we can consider this one. Okay, so we can suddenly remove of this DC. So what will happen here? The receiving end voltage is falls down. This may leads to the voltage sag into the system. Why? Because the huge amount of loads are already connected to these loads. So in this feeder, the more huge amount of loads are connected. One of the source, yes, this is the source. One of the source is suddenly disconnected. What will happen here? This total load is put on the main sources. So this may leads to the increase this percentage voltage regulation. That may be leads to the voltage sag, and leads to the some equipment damages. Equipment damages. So equipment damage. So this is one of the advantage. At the same time, this is one of the. So we are using this DC to improve the voltage regulation, or to solve the voltage regulation issues in the power system. At the same time, it is also because of sudden removal of this DC from this feeder, it may leads to the voltage sag and leads to the equipment damages also. So why voltage sag is happened in the system? Because of suddenly removal of the voltage source, that may leads to the reduction of the voltages in the system. So that's why once you should add this DC to this feeder, you should maintain some techniques. You should maintain some rules and regulations, or you should perform some tests before adding this DC to this feeder. Once this test is passed, then only you can add this disease to this fader. Then only you can remove the all these regulation problems in the system. Okay, what are the different tests you have to perform? What are the measure you have to take while you are connecting this DC to this fader and all other things we will discuss in this. Okay, you can see this. Okay, what are the different tests we are going to perform here? Now these are the some tests. Okay, so yes, how to perform this test? So that is very easy. Okay, yes, how to perform here? A very simple test here. You can see this very simple test. I will explain you the test. So before you performing this test and the measures, you can take one example also. You can take uh, one measure here. Or, you can take one precaution here. So once you should remember where you can connect this DC. So for suppose this is substation. This is the substation. This is swing in substation. You can calculate that how much far. So how much distance whether you connected the DC to that substation. Or within the substation we are connected this DC, or how much far it is from substation. So what are the protective schemes to protect this DC and all of this you can calculate it as well as. Okay, so based on this how much distance we are connected to this DC to the from the substation and all other things, we are performing one test called simply the test very easy, because so without addition of the or adding of the DC, what is the total load requirement once you add the DC to the system? Okay, how much it will withstand to how much it will drive the load load percentage, how much it take the load percentage, so all other things you can measure, then after only you can connect the DC to the system. So this is very simply explained in form of the curve, this curve. Okay, very easy curve. We can see, you can observe this curve. You can perform the test. What is the test here? See this. If you can perform the test, this could be a less than 5%, unless there is a fast acting voltage regulation equipment can be counted for change. What is the meaning of this one? So because so I will explain one more example. Vs, simple example. VR, Vs and VR. I can add the DC here in the distribution. Say I can add the DC here. I can add the DC here. What we discussed here in this case, there is some fault in the system. Here, there is some fault in the system. Without fault, this case without fault. This is the fault case. So, but for the same principle, we are considering here. So, for suppose there is an addition of DC to this system, so it will leads to the increase in the performance of the system, or it will drive with some loads. So suddenly we can remove this DC to the system. What will happen here? There are some we can pass the voltage regulation to the some extent. So here the test means here you connected this DC to the system, then you can measure. You can measure. Remember this points. You can measure how much percentage of the load this DC is taken. DC is withstand to take, or DC is capable to take how much percentage. How much sharing of the load will be DC is taken. If you take in less than 5%, here see this region less than in this curve, this region less than 5%. You consider this DC to add into the fader. And if it changes, voltage changes and all other things more than 5%, you are not connected this DC to the system, and it is not preferable to add this DC to the system. How to calculate the percentage that voltage change? How to calculate that one? So how to take the measure as this measure as a quantity? How to take means here. So when you when you add this DC to the system, so you can suddenly remove this DC. If you, on that removing case, how much amount of voltage is fall in this VR? So how, at the same time we can calculate the voltage regulation. That this is yes. So on the time how much speed, how fast the voltage regulation equipment to uh, activate to clear the fault. This is the first case. What is the first case? How what is the voltage change while you are while the DC is removed from the system? First case. Then what is the second one? How fast our voltage regulation equipment to protect the system from this lower level voltages? So this will not reaches to the more than 5%. It will be in this region. See this region. So your considered DC is added to the feeder. Otherwise, you can remove this feeder. So these are the some solutions you can see this. Yes. So what is the meaning of this first one? You can add the, you can disconnect the DC. This may not be practical to widespread region. So commercial roads and all other transmission. So that the change, you can disconnect the DC. The change should not be more than 5%. So what is second one? Installing more voltage regulators with the capability to bypass the normal time delay of 30 to 40 seconds to begin changing immediately. So what is the third one? The important one. So it will take the DC to take the decision to operate. So for suppose, as I said in the last class, so last class in this, so in this one, reclosing, we are already discussing that. So different protective scheme for, so different protective scheme for DC as well as the police feeders. They are separate protection scheme for both feeder as well as the DC. Different protective schemes are available. They not only protect the system from the fault. Similarly, in this case also, so here in this protective schema of this DC, whenever there is some problem in the system, it can withstand up to the 5 minutes. It can withstand up to the 5 minutes time. Maybe in that 5 minutes time, what will happen here? Maybe the recloser is operated to clear the fault, or fuse may be melted, or regulation equipment may be to clear the fault and all. So this is the one condition that it may be withstand, or it may be connected even though there is a problem in the system up to the 5 minutes. So next one, what is the third one? Fourth one, limit the amount of diesel transfer. Okay, so now one another problem here we are going to discuss here. One another problem at the same time, the voltage regulation. For suppose we have the uh, uh, some more different types of voltage regulators to improve the voltage regulation. So on the voltage regulation, for suppose you can consider this DC. See this DC. Yes, you can see this. You can observe this DC. Okay, this DC is connected. Remember, yes, DC is connected on the voltage regulation switch side. Remember this side. So this is the transformer, regulator transformer. One side is connected to the fader, and the other side is connected to the DC. So what will happen here if there is any fault in the system? What is the net power? Net power. Here, what will happen? Net power. Now, going to see this. Voltage regulator commonly comes with a reverse power feature that will allow the regulator to be used in the failure to supply from its alternate source. So what is the logic behind that one here? This is the logic. To the net power through this voltage regulator is in the reverse direction. So the voltage regulation controls switches direction and regulates the original source. So this is one of the operating component because of user. It's very simple. So this voltage regulation direction power direction is like this. Net power through this direction. So there is any fault in this one. There is a reverse tap current in this one. So the current direction changes is like this. So what will happen here? We can prevent this problem. So here we can use this method. So regulation vendors come up with their configuration switches and control that it can be detect this condition. The result is to keep the regulator looking in the forward direction. So keep the regulator looking in the forward direction. The line drop compensator, remember the line drop compensator setting may be changed to the reverse condition exists. Yeah, as I said, there is a fault in this one. So under normal conditions, it is like this. There is any fault, this may be a current reversal in this direction. So but our what is our aim here? The regulation is in this direction. So that's why to remove this one, this one to reversal of this power and other things, we given up with a solution called line drop compensator R and X setting may be changed to the while the reversal power condition exists. So this settings we have changed. So at the same time, now see this what we discussed here. So to improve this power quality, yes, to improve the power quality, we are connecting DCs to this distributed side as well, some load sets. Here, based on the type of the DC, okay, based on the series based on the type of this DC, okay, the power, the improving of this voltage regulation is changed. For suppose we are using solar DC as a solar, the impact is one way. For suppose we are adding a wind energy, this is the wind energy, the impact on this voltage regulation is another way. Because the solar is works on the morning time, this wind mills are more preferably gives the amount of power in night time. So at the same time, so one question is here, as I asked them at the starting of the lesson. That is, so you should remember one thing, where you can connect this DCs. That means here it is connected the DC near to the substation or very far away from the substation. Based on that one also, the voltage regulation changes. So, so this is one of the problem. So at the same time, in the load side or in the substation side, someone they can add the some this capacitors banks to improve the power quality or to improve the power factor that may leads to the improve of the power quality. So that will also greatly impacted by adding this disease to the distributed generations. Okay, one thing you should remember here, you should know that whether you add which type of DC to the feeder. Once you decide that which type of DC are added, then you can decide that what is the load sharing capability of the DC. You can run the some test and all other things. Once it is successful, you can add the DC to the systems. Okay, what is the next one? Next topic is harmonics. You know that harmonics are very dangerous, very common to the power system because of increasing of the harmonics in the system. That may leads to the heat generation, more heat generation in the any machinery or any equipment. that may leads to the damage of the insulation, that may leads to the damage of the equipment also. That's why harmonics are very important in the power system. So there are some different techniques to calculate the harmonics, total harmonic distortion, total demand distortion, and all other things. So harmonics is nothing but the waveform that is more than the frequency levels we can calculate as a harmonics. Now you see this harmonics F is equal to the fundamental harmonics, Fs is equal to 50 Hz. That is the normal frequency. If more than that 50 Hz, we can call it as the harmonics. So that order we can measure in 1, 2, 3, and so on, and third also. So here we are in the discussion of the distributed generations. So how these harmonics are produced into the system because of adding operating power. Here our topic is operating power. How these harmonics are produced in the system while you add the disease to the system, a power system. You know that. So when I'm here in this our topic, the production of the harmonic means we are using solar type of the DC. So what is solar energy is the DC, direct current. So but which type of power we are using here? AC. So you are connecting DC to the AC, you are using the some converters. Which type of converter? That means the power electronic converters. So by this power electronic current on and off cases of these switches, like the IGBTs, MOSFETs, and thyristors, some diodes, and all other things that may lead to the production of the harmonics into the system. That will be defined by the IEEE standards also. So what is the harmonics? What is the harmonical frequency? What is the normal frequency? So how to calculate that harmonics? Then based on the performance, what is the impact of the system and all other things will be given by the IEEE standards 519 and 1992. Okay, so how to eliminate this DGs into the system? So this harmonics here in this diagram they can discuss in the third order harmonics. Yes, this is the order of the third order. So yes, because of this some thyristor based power converters and all other things, there are some amount of harmonics are injected into the dynamos. How to reduce that harmonics into the system? To improve the to use the several different types of PWM techniques, but pulse width modulation technique to reduce the harmonics and to increase the performance of the converter. Okay, so not only that the harmonics is produced by the converters, I think power electronic devices, there are some possibility that this transformers is also produced with some harmonics. Okay, okay. In the next class, okay, we are going to continue the remaining topic. Okay, thank you for joining today's class. Thank you. Thank you.